Image. This is the Lomonosov spacecraft. View more. Credit Mikhail Panasiuk. The Lomonosov project is a larger-scale scientific and educational space project of Lomonosov Moscow State University aimed at studying space phenomena. In the course of operation of Lomonosov satellite on the orbit, the team of Skobeltsin Scientific and Research Institute of Nuclear Physics (MSU) received new data on many understudied physical phenomena both in the universe and in the atmosphere of the Earth. The results of the studies were published in such high-rating magazines as Journal of Cosmology and Astroparticle Physics and Space Science Reviews. The Lomonosov satellite is the project of Lomonosov Moscow State University, launched to commemorate the 360th anniversary of its founder's birth. The satellite entered the orbit of the Earth in April 2016 to study high-energy space rays and high-speed processes in the optic, X-ray, and gamma-ray ranges that take place in the universe and in the upper layers of our planet's atmosphere. The equipment installed on the satellite allowed the scientists to monitor potentially dangerous space objects of natural and anthropogenic origin, such as small celestial bodies, asteroids, and space garbage. We've conducted correlated ground and space measurements of a gamma-ray burst both in optical and gamma ranges using the satellite and master the ground network of robotic telescopes operated by MSU. Given the modern level of space research development, ground gamma observatories are very important for high-energy studies and are considered valuable additions to space experiments, said Mikhail Panasiuk, a co-author of the article, Doctor of Physics and Mathematics, and Director of Skobeltsin Scientific and Research Institute of Nuclear Physics, MSU. Space rays are fluxes of particles, mainly protons with high energy, that fill in the interstellar space. Modern science is especially interested in studying the origins, chemical composition, and energy spectrum of high-energy space rays about 1019-1020 electron volts. It's very difficult to measure them from the ground because such particles are very rare. On average, one particle occurs on a 1 square kilometer site once in 100 years. MSU physicists were the first to conduct experiments to register high-energy rays in the upper layers of Earth's atmosphere using a telescope installed on Lomonosov satellite. When entering the atmosphere, high-energy rays react with it and cause air showers, cascades of secondary particles, and strong short-term UV bursts. TUS tracking device. Orbit-based telescope uses the atmosphere of the Earth as a huge target on which the reaction with high-energy space rays takes place. For instance, scientists managed to considerably increase the effective survey area compared to ground installations. TUS registers UV flashes caused by secondary particles in air showers and registers the number of photons based on which the energy of primary particles is calculated. Right now the Russian team is on the stage of analyzing the data collected by the orbit-based telescope within the first several months of its operation. In the future, this data will help the scientists understand the nature and mechanisms of acceleration of high-energy particles. Besides the flashes caused by high-energy space rays, the telescope registered other atmospheric events that manifested themselves in the UV range. The most interesting of them are transient light phenomena, short-term from 1 to 1/100th of milliseconds flashes of electromagnetic radiation that are allegedly associated with storm areas in the middle and lower layers of the atmosphere. Due to the dissipation of the radiation along the clouds, transients give a simultaneous UV signal in the whole vision range of TUS. On the one hand, events like this create disturbances when the telescope is fulfilling its main task, which is the registration of high-energy space rays. On the other hand, they pose an independent topical experimental problem: investigation of the physical nature of transient radiation phenomena and their association with storm electricity. A set of equipment consisting of 3 devices, BDRG, shock, and UFFO, was installed by the team of researchers on board of Lomonosov spacecraft. The purpose of the equipment was to study gamma-ray bursts. A gamma-ray burst is the short-term expansion of a gamma quantum flux to energies that are equal at least to 109 electron volts. The amount of energy produced in the course of such bursts is practically the same to that emitted by a supernova explosion, but the burst takes only 1 second. These phenomena are considered one of the most powerful in the universe, but they are still understudied. In order to clearly understand the nature of gamma-ray bursts, observations should be made simultaneously in optic and gamma ranges. However, it is very difficult to register optic radiation at the moment of its occurrence, as no one can predict in which area of the sky it is to take place. The equipment of Lomonosov spacecraft managed to register optic radiation precisely at the moment of gamma-ray bursts for the first time in history. BDRG, a set of X-ray and gamma-ray detectors, consists of 3 gamma quantum detectors with perpendicular axes. 3G measurements allow the device to establish precise coordinates of a burst source. When a phenomenon is registered, BDRG send a special trigger signal to wide-angle optic camera's shock. When the signal is registered, the system memorizes the optic image of the space area in which the burst took place, and information is transferred to the global network for ground telescopes to be focused on it. Another device called UFFO Ultra-Fast Flash Observatory reacts to the trigger signal by turning on an X-ray telescope to register the burst in the yellow X-ray range. Moreover, it quickly focuses an optic telescope on the location of the phenomenon. Experiments helped the team to reach the record-setting focusing time of about 1 minute. Within the period from its launch to August 2017, Lomonosov had registered 20 gamma-ray bursts of space origin, as well as the bursts from magnetars neutron stars with very strong magnetic fields. The data received from the satellite are unique and cover a wide range of wavelengths: optic, X-ray, and gamma. The Russian team believes that this information will help it make a huge step to understanding the understudied phenomenon of gamma-ray bursts. Within the framework of Lomonosov project, MSU specialists of their own initiative developed and successfully tested Lomonosov spacecraft, a prototype device for the space segment of optic monitoring of potentially dangerous space objects of natural and anthropogenic origin in the near space, added Mikhail Panasiuk. During the design of equipment and onboard systems for Lomonosov satellite, the scientists used cutting-edge developments in electronics, nuclear and physical methodology, optical means of monitoring, and software. Some of these developments are exclusive and have no analogues in the world. The work on the project was performed by specialists, students, and postgraduates of Skobeltsin Scientific and Research Institute of Nuclear Physics, Sternberg Astronomical Institute, Scientific and Research Institute of Mechanics, Institute of Mathematical Studies of Complex Systems, and the Faculty of Mechanics and Mathematics of Lomonosov Moscow State University. They worked in cooperation with scientists from All-Russian Scientific Research Institute of Electromechanics Corporation JSC, Joint Institute for Nuclear Research, Sungkyunkwan University South Korea, University of California in Los Angeles, and University of Puebla, Mexico. Based on the experience gained in the course of satellite development and achieved results, the team embarked on the fulfillment of the next project called UNIVERSATSOCRAT Alerting System for Space Radiation, Asteroid, and Anthropogenic Threats. This project provides for the creation of a group of small satellites for monitoring, identification, and immediate forecasting of natural and anthropogenic space threats. It includes monitoring of the radiological situation, electromagnetic transients, and potentially dangerous natural asteroids, meteors and anthropogenic space garbage objects in the near space in real time. Disclaimer: AAAS and EurekAlert are not responsible for the accuracy of news releases posted to EurekAlert by contributing institutions or for the use of any information through the EurekAlert system.